Questions on homework?
Number 7.
What, second edition?
Second.
Okay, what does that say?
So it says that when the limit x and y approach 0 and 0, the function is y squared
Sine squared x
over x to the 4th over x to the power 4 plus y to the power 4.
So it just asks you to find the limit or show it doesn't exist, right? Okay, ideas?
Well, this wasn't my problem in the homework, but when I saw it on Brian's homework, I thought, what if you use y equals x, and then replace it so that it's x squared sine squared x over x to the 4th plus x.
Okay, so you go along y equals x. So I call this L, and then L would be equal to the limit as xx approaches 0, 0 of, this would give you x squared sine squared x over now 2x to the 4th, right?
Right.
Which this would cancel with that.
I have a question.
And what's that?
So,
It's a half,
okay, that was my question.
right? Since, as you may recall from calculus 2, the limit as x approaches 0 of sine x over x is 1. Right? So you have sine x squared over x squared. It's just 1 squared. And that's it. So you get a half that way. And the other way is obviously along y equals 0. Along y equals 0, your L is just 0. And so limit does not exist. Other questions? Did someone say something? 15?
Yeah.
Second edition? Okay, which one is that? Okay, ideas? Okay, so the trick was when you have 3 variables, you can actually fix 2 at a time, right? So you can decide to, say, go along the z axis, right? Which means that you can fix both x and y equal to 0, right? And in that case, you'd have the limit would be equal to 0, 0 with z. You just have 0 to z to the 4th, right? So you get 0 from that path, right? So what's another path you could choose? You can let y equal z squared, right? Which also goes through the origin. And x equals z squared. Right? So notice that you're actually traveling along the vector curve that looks like t squared comma t squared comma t. Right? That's the curve you're actually traveling along, and it does pass through the origin, right? In particular when t equals 0. And so in that case, L, if I call this limit L will be equal to the limit of z squared comma z approaches 0, 0, 0. Now I replace all these guys with z squared. So this will give me z to the 4th. This will give me z to the 4th. This will give me z to the 4th. Over each of these will be z to the 4th as well. Well, that limit is 1. So again, does not exist. I think most of these doesn't exist. Those are the easy ones. Yeah.
If you've done this along y equals z squared and x equals 0, does it have to be the same?
Yes, because that curve also passes through 0. Right, so x equals 0 means you're in the yz plane, and then you travel along the curve y equals z squared in that plane. it would still go through the origin. Other questions? Second addition as well?
First. Limit as xy approaches 0, 0. Xy over square root of x squared.
Okay, ideas? Okay, so you tried to let y equals x. So along y equals x, we would have the limit of x. X squared over, this would be the radical of 2x. Yeah. But I mean, it will go to 0 because you have an extra factor of x.
All the obvious ones go to 0.
Huh?
When you come down to 0, there's 0.
No, you do cancel an x. Right? This is actually equal to plus or minus the limit of x over radical 2. Plus or minus because of the absolute value. If you're approaching from the left that x is negative, it would give you negative x. If you're approaching from x is positive, you get positive x. So yeah, you still get 0 at the end of the day. Yeah?
We need to use the squeeze theorem.
Squeeze theorem. All the obvious paths would actually give you 0. So then you're trying to think, maybe the limit actually is 0. So we could use the squeeze theorem. We show L equals 0. So the squeeze theorem says in absolute value, I'm going to put this minus. Better mark this one. Okay, so we have that. All right, so how did you finish that one?
I said x would be less than or equal to the absolute value of x squared.
Oh, you got rid of the y squared?
Yeah, and that just gives you y, the absolute value of y.
Right, so. Right, so technically this gives you xy over, this is absolute value of x, but you're already in absolute values, it actually doesn't make a difference. So it's just xy over x, which is just y, which approaches 0 as xy approaches the origin. Therefore, L equals 0 by squeeze theorem. Can anyone think of another way to do this? You could use polar coordinates as well. You could say using polar coordinates. Then this limit would be equal to the limit as r approaches 0 of, you replace x with r cosine theta, y with r sine theta, you would end up with r squared cosine theta sine theta divided by r. This would cancel into that, and as r goes to 0, you also get 0.
The question was the squeeze theorem. If we're like, when we're looking for a function g of x that's larger or equal to,
Yeah.
what if we just identify a function that whose limit goes to 0, but there is one? Like, we just do that by inspection, sort of, right?
Yeah, I mean, the way you'd approach it is, You want to get a fraction where it's just a slight tweak of the original one, so you shouldn't have to look very far. So you just want to sort of tweak this, maybe make the denominator smaller, the numerator bigger. That's sort of what we're going to do. I mean, we won't cover any really confusing cases here. If you're familiar with the algebra of fractions, it should be fairly straightforward how to do it. The main problem would be to recognize when you should be trying this, right? When you know you tried all the convenient paths, you're pretty sure that, you know, it should exist. Other questions? 14 and 13.
So we've got a numerator of x squared plus y squared. And a denominator of square root x squared plus y squared plus 1. Then at end of the square root minus that.
Oh, okay.
And then you take the limit as it goes to.
Okay. We tried that. Yeah?
Multiply by the conjugate.
To multiply by the conjugate. You could actually do a polar, but it's not super necessary. I mean, you could do that just to write less, but that's all it's going to give you, really. Let's do that so I won't have to write so much. Right, but pretty much what we're doing with r squared, just imagine you can carry x squared plus y squared along like that. And yeah, as someone said, multiplying by the conjugate would be the way to go. So it's going to be x squared plus 1 over r squared plus 1 plus 1. The denominator becomes the difference of two squares, so you just square this minus the square of that. So the denominator is just r squared plus 1 minus 1. This would be r squared times the radical of r squared plus 1 plus 1. And so, of course, the minus 1 and this cancels, and then you can cancel the r squared, so you really don't have that left. And then you plug in r equals 0. The answer is 2. Right, so multiply by the conjugate over itself was the answer here. Yep.
Number 27 and the first division.
27. Did I assign that?
Yeah.
27, first edition. What does it say?
F of x.
That thing?
Yeah.
X squared times y cubed over 2x squared plus y squared. If x comma y does not equal 0 comma 0, the bottom is 1. If x comma y equals 0 comma 0.
Okay. Continuous or not? Not. Check the limit as xy approaches 0, 0 of x squared plus y cubed over 2x squared plus y squared along x equals 0. Call this L. You get L equals 0. In particular, it's not equal to 1. So not close. Notice here, I didn't actually find the limit because I didn't need to, because note, we did not actually find the limit since if it did exist, it would have to. Why did I not continue and figure out does limit exist or not?
Oh.
Right? Along one path I got 0, right? It means that suppose the limit existed. What would that mean? It would have to be 0, right? So if the limit did exist, it would have to be 0.
Alright.
This tells me it's 1, so it doesn't work. If it doesn't exist, then it doesn't exist. It's still not continuous anyway. So I didn't even need to complete finding the limit. Once I found a path that didn't match that number, I'm done. Right? Because whether it exists or not in that case, it's not continuous.
Number
Yes.
27?
I suppose the second edition?
Yes.
Is it the same thing? Is it a different?
It's similar. But the answer in the back of the book is really different from what I got.
Is it not this?
It is.
It's a completely different problem?
No.
Or-
Same thing. Same thing.
Oh,
But the answer is that it's continuous if you the original is not equal to 0, 0. The xy is not equal to 0, 0 is continuous.
oh, it was without this thing. What
No, it's
The exact same.
it's the exact same thing, but it's got a different answer in the book.
Yeah.
It says x, y is not
The answer say
Yeah.
x equal to 0, 0.
Hang on.
What?
The same problem.
If it's the
The
same
answer-
problem, it's not continuous. I don't know.
Okay.
It says for the second one, but it says 1 of x, y is not equal to 0, not really equal to 0, 0.
No.
No, it says in the text.
I have the
Okay.
I don't. It would make sense for them to say the not equal the origin here because you divide by 0. That would make sense.
So I wrote it down wrong.
And then,
He's just saying that f of xy is discontinuous at 0, 0, right? So then.
Right. So what was the
domain
question?
Or whatever. If they wanted to do
how is the question phrased? That's important.
Determine the set of points.
Determine the set of points where it's continuous. Okay, so we have found that it's not continuous at 0, at the origin. Okay, so now we can finish. So the domain, the set where it is continuous would be all x, y such that right? Now, as long as we're not at the origin, each of our functions are continuous, right? Only the origin where they are stitched together, that's the problem. So ultimately, this would be your answer, and this is why 0, 0 doesn't work. First edition, second edition? Yeah, so it's important to know what you're asked for.
Okay, the question says that the limit xy equals 0, 0 is x cubed plus y cubed over x squared plus y squared.
Hold on. X 0, 0, x cubed plus y cubed.
Over x squared plus y squared.
Okay.
And it says use polar coordinates to find the limit.
Okay. Since we're bipolar, no pun intended. Okay, so if we're bipolar, what would we do?
Write x squared plus y squared as r squared.
So x cubed plus y cubed would be what? This is just r squared. What would the top be?
R cosine theta cubed.
Right. R cubed cosine cubed theta plus r cubed sine cubed theta. In which case, we'd be able to factor out an r cubed. And we go to 0.
Why doesn't it matter what theta is approaching?
Because we're multiplied by 0.
But I
So-
mean, if we were to set up.
This is going to be some constant that we're multiplying by 0. I should mention that in the case where you have a function of theta as the answer to the limit, then this method doesn't give you an answer. Because the fact that theta can be arbitrary sort of
So I can
makes
have a
things weird.
function in R and theta. What that
Right, because it wouldn't be a single limit anymore. You sort of have to treat it like a multivariable function. And then, of course, if r is going to 0, there's no telling whether theta goes to 0 or not. You'd never be able to tell. So there's too much ambiguity if you get a function of theta as your answer. You'd have to get either some constant. If you don't get a constant, you get a function of theta as your answer, it means that this method just doesn't work. Try something else. I suppose that's it. You can pass your homeworks along the tables until they get to the front. Okay, so it turns out in 3 dimensions, because we have 3 dimensions and you can approach a limit at an infinite number of directions, the derivative sort of ends up being weird. If you had, so pretend you're looking at the edge of this paper, right? Right, so we're in 2 dimensions now. You have the edge of the paper, right? So we're in flatland. Now, pretend the edge of the paper is a line, right? Now, back in Calc 2, you can actually find the slope of this line, right? Now, if you look in Calc 3 now, we actually consider the width of the paper as well. So now we're thinking of this as a plane. Notice that you can have the edge staying along a certain line, but the paper itself can tilt, right? So that means like there's some dimension here that we can't really fully address by only looking at the derivative in the Calc 2 sense, right? We can maintain a certain line in one at a constant and in the plane, like in the xy plane, but things can move around above or below the xy plane where we're going to have to be able to account for that. So somehow differentiating with respect to one variable isn't enough in this context. We have to sort of account for the other directions as well. Right, so we can't just say, oh, about the x direction, you have to think, well, what is the y doing, right? Because now it's not a line anymore, it's a whole plane that we're going to be looking at, right? So that's sort of the idea that we're going to be doing with this. And we're actually going to use a notion called partial derivatives. Now there is sort of a notion where you can take into account all the different derivatives in different directions, a finite number, but we're actually not going to cover that. What we're going to be doing is we're going to think of things in one variable at a time, right? So that's why it's called partial derivative. There's no such thing really now as a total derivative, right? Like if you had a function of x, you can say we find the derivative. There is no the derivative anymore. Right? There are too many dimensions to worry about, too many directions you can approach them. So what we do is we can find partial derivatives. And so what we're going to be doing is we're going to find derivatives if we're only considering it as a function of x, or if we're only considering it as a function of y, right? In the x direction, what's the derivative? In the y direction, what's the derivative? And later on, we're going to talk about arbitrary directions, right? What if I'm pointing in that direction? What's the derivative? What if in this direction? What's in this direction? What's in that direction, right? There's so many directions, right? There's no the derivative anymore. Right? So what we're going to cover now is called partial derivatives, where we're really going to dissect things piece by piece. And that's sort of what they're about. So suppose we have f of x, y. We can we may consider this as a function of x only, that y equals a constant, consider that as a function of y only. By doing this, we say we are taking a partial derivative with respect to x. So that's sort of what we're thinking about. Because there's so many directions to think about, we sort of think in the familiar terms, right? In the x direction, what's happening? In the y direction, what's happening? Right? And these are called partial derivatives because we're really taking the function by parts. Look at only the x guys as the variables, the y guys are constant, or look at only the y guys as variables and the x values as constant. And we can actually have a similar definition to what we had before. Let f be a function x and y. The partial derivative in terms or with respect to we have sort of this weird notation. I'm actually going to show you the notation here. You can say f, and you put a little subscript x at the bottom. This is defined as the limit as h goes to 0. And you're doing the difference quotient, except you're doing it only with the x. Right? So it's f of x plus h minus f of x all over h. Right? So notice here we're fixing the value of y. Y we're not letting move. We're thinking of it as a constant, but we're taking the derivative in terms of the x only. Right? Similarly, partial derivative with respect to y. Limit h approaches 0 of x plus y. So you're sort of taking the difference quotient, but you're taking it in terms of one variable at a time. Whenever you do this, you start taking a partial derivative. Right? So you can think of it in terms of one variable or the other. And that's And of course, it's if it exists, because after all, this is a limit. The derivative doesn't have to exist. But if it exists, this is how we'd find it. And do I want to some more notation before we move on? In particular, I like this notation, so I tend to use this, but you'd see other notations given, so I just want to mention it. You see something like fx, you could also write it as, similar like how we have dy dx and y prime, you can actually write it like that. But you write a curly d, so it's something like this. You can actually write that, right? Other notations, these are the two most common ones you'll see. Other notations are F1 or D1, things like that. But these are by far the most common ones. Like in our book, they're always going to use one of these two. Right, so it's like a dy dx, except you do a like curvy d. Right? And whenever you write that, everyone knows you're taking a partial derivative. You're thinking of it as a multivariable function, and you're only differentiating in terms of one variable at a time.
So how do you say f1 is with respect to x? So what's
Right.
f2? F2 is like y.
Yes. F2 would be y. And if you have z, you'd call it f3, so on and so forth. You'd number your variables. But these are the two most common ones. I like writing this because it's less marks to put down on the paper. Computationally, these work with all the derivative rules before. Just consider all variables but the one with differentiating with respect as constants. Right, so luckily you can go and you can reprove all your differentiation rules using multivariable functions, but we're allowed to use a shortcut right away, and let me show you how it would look. Example, find the first partial derivatives of f of xy equals 3x squared minus 2x cubed y plus 3xy cubed minus 2. Also evaluate fx 0 and f of Okay, so by the first partial derivatives, whenever you see that, they mean they want you to find with respect to x and y. And if it were three variables, like a z, also fz. You can't do this. Okay, so how do we move on? Fx equals. Okay, so the trick is, remember, when you're doing fx, everywhere you see a y, it's now a constant. Might as well be 2 or pi or 7. It's a number now. Y does not move, it's constant. Everything you see y, it's a constant, right? Only x is the variable. So if you're going through and you differentiate this, you would have 3x squared, you differentiate that. 6x. What's the derivative of this?
6x squared y.
Minus 6x squared y, right? Because you just have a constant times x cubed. You differentiate x cubed, you leave the constants alone, right? That's how you differentiate those. Plus 3y cubed, right? Because derivative of x is 1, these are constants, they just stay, right?
Constant.
0. That has no x's in it. It's a constant. Derivative is 0. That's the partial with respect to x. Right? Which would mean fx of minus 1 comma 0 is actually equal to
Minus 6.
minus 6,
Plus 6.
well, minus 0 plus 0, right? So it's just minus 6. In other words, you're saying when you're on this function, if you're at this point and you want to find the slope in the x direction, it's minus 6. Okay, what's fy? F sub y, or partial with respect to what?
Partial with respect to y.
So if we're differentiating with respect to y, the derivative of 3x squared is? 0, because there's no y's in it, it's a constant. Derivative of 2x cubed y?
3x squared.
Huh?
Minus 2x.
Minus 2x cubed, right? Because you have a constant times a variable, the derivative is just a constant. What else?
9xy squared. Minus 8y cubed.
Fy of 1, 1 is equal to, now you just plug in x equals 1, y equals 1, so it's minus 2 plus 9 minus 8. Right, so that's minus 1. Does everyone get it? So the idea is if you're finding partial with respect to x, think of y as a constant, differentiate normally, right? Just imagine that y is a constant. And if you're doing with respect to y, x is the constant, right? Just think of it like pi. You know, if you're differentiating pi x, the answer is pi. Differentiating pi x cubed, the answer is 3 pi x squared, right? That's, you leave the pi there. It doesn't move. Right? That's sort of the same thing.
The
Yes.
first partial derivative, that just means the first derivative of the two things.
That's the first derivative with respect
So
to
you can have a
x.
second and
We can do second and thirds and fourth derivatives, yes. We'll get there soon. Let's see. Well, I drew a little illustration here to sort of tell you where we're going. So if we had so we have some function here, like some surface. Right, this is our z equals f of xy. Right? And I'll say I'm here. I'm at the point x0, y0. Right? Now, if at that point I find the partial derivative with respect to x, what am I actually doing? It means I'm actually slicing into this thing with a plane that's parallel to the xz plane, right? I'm cutting through this with a line in the x direction, right? Now, whatever the slope of the tangent line is at that point in that direction is going to be my fx at that point. Right, but you just think of a plane slicing through where the plane is parallel to the xz plane, and then if you drew the tangent line on the curve at the point, you'd get actually fx, right? If you cut in the direction of the y, that would give you the fy. And I don't know if you can see where we're going right now. I'd be able to have two directions, and I would be able to define a plane by those two directions, right? So eventually you're going to be seeing that we're going to be able to find tangent planes to surfaces, right? Just like in Calc 2 you're finding tangent lines to curves, we're going to be finding tangent planes to surfaces, and our partial derivatives are going to be the ones that help us do this. But that's sort of the idea of what we're doing, right? That's the picture behind it, right? So you slice it with a plane that moves in the x direction, and the tangent line at that point, its slope is going to be given by the partial with respect to x. You slice it with a plane that's parallel to the y direction, the slope of the tangent line at that point is given by fy. That's what they mean, sort of, in physical reality.
Hope we're not have to draw it on a test. It's not hard.
Give them like this.
No. We're going to ask you to find tangent planes all the time. I'm not going to ask you to draw them. We're going to be drawing other stuff later on. Of course, all Right, I'm talking about things like product rule, quotient rule, chain rule. let's see who remembers the product rule. How do we differentiate this? Fx.
So it's y squared e to the xy. Plus 1 over y sine, cos x over y.
Alright, think you got away. How about that one? X, y, e to the xy plus
Plus e to the xy.
X, L, and y.
plus e to the xy. Right, you have to apply the product rule here, because e to the xy and y are both functions of y. You have to use the product rule here. Right? In the first case we didn't because y was a constant, so we just hung around. Now,
X, L, and y. Times sine, times
X over y squared. Cosine.
alright, derivative of x over y is minus x over y squared times cosine of x over y. Implicit differentiation, remember this?
Yes. Unfortunately.
Alright, sort of that things where if you had x and y, whenever you differentiate y, you attach a y prime to it because of the chain rule. We're not going over the process here. I expect you guys to remember that. So what would this be? I'm finding the partial of z with respect to x.
Oh, so
2
2x.
x y prime.
First times derivative, second plus second times.
Partial with respect to x means that your y is a constant.
Oh.
Okay.
Right. Your z is a function of x and y, which means you can actually differentiate. The z, you're going to have to sort of attach a sort of z prime, but it's not. Yeah. So now how do we move on?
Plus 2 z.
2x times z prime.
2x times z prime, which is partial of z with respect to x, right? Because we can't use prime notation anymore, because you won't know who's the variable you're differentiating with respect to, right? If I just say z prime, is it with the x or the y, right? So you have to actually use that, or you could put the z with a little subscript x, right? Either one is fine. Okay, and then how do we continue? Plus 2z, because you have to do the product rule. This one? This one? X, y, partial, plus zero. And now all we want to do is solve for this guy. In the future chapter, we're actually going to, I think it's 11.5, we're actually going to find a shortcut to doing this whole thing. We're going to realize we're going to be able to do this a lot easier. But for now, this is how we know how to do it. So at this point, we have 2x minus 6z plus xy, all that times partial z with respect to x, equals, now I'm going to bring everything over the other side, so this is minus 2xy plus 2z. So that would be the partial of z with respect to x. One more example before we take a break. So right now I'm just going through all the old familiar kinds of things you would do with derivatives and I'm showing you that here they're not so different. You just have to know when to think of someone as a constant, when to not. like I was mentioning before, the notation is actually generalized. So with x and y, we can also have z. So here I'm going to actually define fx, fy, z first. Partials. F of x, y, z is equal to x e to the z plus ln of x, y, z. After this, we'll take a 10-minute break and then switch to the other class. If x equals what?
Z 1 over x, y, z times y, z.
Right? yz over x, y, z, which is, you can actually simplify that.
1 over x.
Fy,
1 over x, y, z times x, z. 1 over
y, fz,
z x e to the x.
nope,
E to the z. Z times x.
yeah,
No,
that,
x times e to the e to the
yeah, that doesn't change. The constant times the function. And this, of course, would be xy over x, y, z, which you can write as x e to the z plus 1 to the z. So that's the answer there, that's the answer here. Not so bad, right? Don't worry, it gets more interesting. Don't get bored or anything. All right, we'll switch to the next class now.